So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now.
Assalamu alaikum warahmatullahi wabarakatuh. How are you guys? I hope you are doing fine. So today we would be starting a new topic, that is 5.2 radioactivity. In our previous lecture we covered section 5.1, the nuclear model of an atom, and today we would be moving on to 5.2 radioactivity. Now this topic is a little detailed as compared to 5.1, so it's likely that I'll be needing to divide this lecture up into two parts so that you guys do not get bored while listening to me. The first thing in this is a radioactivity. What exactly is a radioactivity? So let's get down and discuss what is the concept of radioactivity. So as we have discussed in our previous lecture, that isotopes are atoms of same element with a different neutron number. So isotopes of an atom can be stable or unstable depending on their nuclear properties. Those isotopes which are unstable, which would be they would like to become stable by emitting energy and by emitting particles so that they can become stable. Such isotopes are known as radioisotopes or radioactive isotopes. A nucleus is unstable if it contains too many neutrons or protons. In that case, the unstable nuclei will try to become more stable by ejecting particles out of it. This process is known as radioactivity. So radioactivity is the process when an unstable nuclei tries to balance itself out. It tries to become stable by emitting particles or by ejecting particles. Radioactive emission of particles from the nucleus of a mass is in form of either alpha particles or beta particles. These two can sometimes be accompanied by emission of energy as well, which is known as gamma rays or gamma radiation. When an atom emits radioactive waves or radioactivity, or either in form of energy or particles, the process is known as radioactive decay. It is always a random and spontaneous reaction, or it is always a random and spontaneous process in which an unstable nuclei will disintegrate into a more stable nuclei by the emission of alpha particles, beta particles, and or gamma radiation. Now alpha particles are basically helium nuclei as they consist of 2 protons and 2 neutrons. Beta particles are fast moving electrons, and gamma radiation or gamma rays are electromagnetic waves of very short wavelength. How do we find out that a specific isotope or a certain element or atom is giving off radiation? For that we use devices which are known as radioactive detectors. Radioactive emissions can be detected by using the following common detectors. You can use photographic detectors. When a radioactive substance is placed near a photographic film coated with silver halide, the latter will produce a similar effect as seen with exposure to visible light. When a photographic plate is exposed to visible light, it leaves traces onto the photographic film, or similarly when radioactive waves or radioactive particles are bombarded onto a photographic plate, it also leaves similar traces or exposure marks on the photographic plate. After the exposure is completed, this latent record of the accumulated exposure can be made visible through a chemical development process. You can develop these photographic plates just like your photographs, and you would have yourself a photograph of a nuclear emission. Just like when you take an X-ray, the X-ray operator, it develops those photographic films, and it would give you a permanent picture of the X-ray of a body part. Okay. The next type of detector that we can use is known as Geiger-Muller tube, or GM tube in short. Now GM tube is the most useful and most common type of radiation detector, which is used for determining the intensity of a beam of radiation, or for counting individual charged particles, like how many times a charged particle was detected by the GM tube. When ionizing radiation enters the tube through the thin mica window, this is one of the part of the GM tube, I'll show it to you on the next slide, it collides with the large argon atoms and ionizes them. These free electrons will accelerate toward anode, causing further ionization of argon atoms during their course. Negative electrons move towards the cathode, which is the positively charged electrode, whereas the positive ions now move towards the anode. This collection of electrons and positive ions on the anode and cathode causes a pulse of current to be formed, which is detected, which is then amplified and fed to a rate meter or a counter, which simply counts it up, and it tells you how many times the ionization occurred inside the Geiger-Muller tube or the GM tube. So basically this is the structure of a GM tube. It's a hollow tube which is filled with argon atoms, and in between it has an anode, a thin silver wire anode or a thin wire anode, and this is known as a mica window. This is covered mostly with a coating, so that only a specific amount of radiation is able to enter over here. And then over here is the cathode on the side of the tube, and when ionization rays, whatever they are, either alpha particles or beta particles, when they enter over here, they ionizes the argon molecules, argon atoms, which causes the flow of negative and positive charges towards these two cathodes and anodes, which causes a surge in the electrical current, which produces an electrical current. That current is amplified and fed to this counter, which counts how many pulses occurred by a certain source, by a certain radioactive source. Another type of detector we use is known as the diffusion cloud chamber. Again, this is one of the more common types of detector being used. When emissions from radioactive substances are allowed to come into contact with air molecules, they will tend to knock out the electrons from those molecules along their path, and that would cause a path of ionization to occur. The diffusion cloud chamber is the device for making those paths visible so that you can see them from your naked eye. They consist of a container containing air. At the top of the chamber, a row of felt strip is soaked in ethanol and they are placed on the top of the chamber, whereas the lower part of chamber is cooled by solid carbon dioxide or liquid helium. This causes the alcohol to evaporate into vapors and continuously diffuse downwards. It then becomes supersaturated at the center of the cloud chamber. It means the air is holding more vapors than it technically should, or the number of vapors it normally can hold. When emissions from the radioactive substance are placed in the chamber, the emission will cause ionization along its paths. The ionized air molecule will attract the vapor molecules and become too heavy to stay in suspension, and thus those air molecules would condense into tiny liquid droplets along the path of the emission. This would cause, on the screen of the on the top glass, if you look from the top glass surface inside the diffusion cloud chamber, you would see emission lines like this formed on the vapor cloud in the middle of the cloud chamber. Alpha particles usually cause thin and long rays of lines. If the track of ionization radiation in a cloud chamber can be reduced by using the or by comparing these images to a known pattern, alpha particles usually cause, if you have a source that is emitting alpha particles, then alpha particles usually start at the source and they spread out in all direction, having thick but short lines, or thick and short patterns that would be diverging in all directions. Whereas if the source is emitting beta particles, then the track you see on the diffusion cloud chamber would have long, thin, wiggly lines on the screen. In case of beta particle, you usually would not see a widespread exposure or a widespread image as in form of alpha particles. This is to give you an idea of what type of emission lines or patterns alpha and beta particle produce inside a diffusion cloud chamber. Count rate. Count rate is the number of decays per second recorded by a detector and recorded by the counter. So the number of times an emission is occurs and is detected by a detector in 1 second, that is known as your count rate. It is measured in counts per second or counts per minute. The count rate decreases the further the detector is from the source, and alternatively it would increase the closer you would bring the source to your detector, whether it is whatever type of detector it is. This is because the radiation becomes more spread out the further away it is from the source. As you can see from the pattern, radiations usually spread out in all directions. It doesn't usually walk in a straight line like a beam of light. Background radiation. Background radiation is the naturally occurring radioactivity which is present due to many environmental factors. The GM tube usually detects from 20 to 60 counts per minute without any radioactive source nearby. This is due to background radiation. Background radiation is produced by tiny fragments of radioactive elements which are present naturally in all rocks and soil, the atmosphere, and even in living material itself. There is a theory that ever since the nuclear explosions and the dropping of atomic bombs, the atmosphere has been clouded with radioactive particles since then, and due to the blasting of radioactive material, due to the blasting of atomic bombs in World War, our atmosphere has been contaminated by radioactive material, and those radioactive fragments have become a permanent part of our atmosphere for hundreds of years more to come. So they technically are all over the globe. They have become a part of our environment and our atmosphere. Apart from that, we do have natural sources of radioactivity as well, such as the cosmic rays from the sun. The earth is continuously bombarded by high-speed particles from outer space and from the sun. The cosmic rays, they are also a major source of radioactive emission or background count. Then we have a lot of natural radioactive elements such as radioactive gas radon, which may accumulate in buildings, so increasing the local background count. Even your concrete and cement buildings, weapons testing, and these type of things also accumulate towards background count. Whenever you're taking reading in a question with GM tube, you should always minus the background count so that you get an error-free reading, so that you avoid the systematic error, which is known as corrected count rate. Radioactive decay. Radioactive decay refers to the process in which alpha particles and beta particles are emitted by an unstable nuclei of an element in order to form a more stable nuclei. This image depicts the process. The starting nuclei or the decaying nuclei is also known as the parent nuclei, which produces an alpha particle or a beta particle and decays into another type of atom, which is known as the daughter nuclei. This was a uranium nuclei, uranium-238, and when it emitted 2 neutrons and 2 protons or a single alpha particle, it became the daughter nucleus of thorium-234, as 4 particles have emitted out of it. So the number 238, the mass number 238, now becomes the mass number 234. Decay processes are always written in form of an equation. In equation, the parent nucleide X, which is unstable, changes into a daughter nucleide along with the emission of alpha or beta particles or gamma rays. This is how you write the symbol for gamma ray. This is how you write the symbol for beta and for alpha. Radioactivity is not affected by chemical reactions or any change in physical conditions such as temperature, pressure, electric or magnetic field, etc. All the nuclei of a radioactive substance have the same probability of undergoing radioactive decay. It is impossible to tell which nuclei will be the next in line to decay or how long it will take to decay completely. Hence, it is totally random. Like we discussed before, radioactivity is always spontaneous and random. Since it is independent of external conditions, the breakdown within the nucleus is completely random. But it is noticed that with many repeated observations of this random process, the average of its radioactive emission does follow some statistical law. You can calculate approximately how much of a basket of radioactive materials will decay in X amount of time, such as X number of hours or X number of minutes. Therefore, the emission of radiation is considered as both spontaneous and random in direction and nature. There are 3 possible types of radioactive emission which can occur when a particle would decay or when a particle would undergo radioactive decay. The first type is known as alpha decay or alpha particles. An alpha particle can be represented as 4,2He. This 4 would be written as the superscript and this 2 would be written as subscript, or can also be written as 4,2 and the sign for alpha particle. When a nucleus decays, something like this, it would be written something like this. When a nuclear decays by alpha emission, the proton number or atomic number Z decreases by 2 and its mass number decreases by 4. If you had an element named X and it had a mass number by the name of A and a proton number or atomic number by Z, and you have to find its daughter nuclei, then you will simply do this. You will minus 4 from the mass number and 2 from the atomic number, and you will know what what daughter nuclei you are having, and along with that you are going to have some energy as well as a helium nuclei or alpha particle. For example, if radon 226 emits alpha particle, it would become this Y, having these atomic and mass numbers, whereas these two things would remain constant. Beta particle or beta decay is written like this, and we give it a -1 charge because beta particles are simply fast moving electrons. In a beta decay, neutron number A remains unchanged, but the atomic number Z increases by 1. During this process, a neutron splits into a proton, an electron, and energy. The proton number now increases because the neutron becomes a proton. The new electron is expelled as a beta particle. If you had an element with the mass number A and the proton number Z, then after beta decay its A would remain the same, whereas its Z, the atomic number, will have +1, whereas an electron and energy would be released. Like if sodium 24 would undergo beta decay, it would become magnesium with a proton number 12, but having the same mass number, that is 24, so this would technically be an isotope of magnesium. Plus a beta particle would be released, that would be a single electron along with a lot of energy. The last type of radioactive emission is the gamma radiation. It has no effect on nucleon number or proton number, it is pure energy. These are usually emitted at the same time as alpha or beta particles. With some nuclides, the emission of alpha and beta particles leave the electrons and neutrons in an excited state. Those protons and neutrons, in order to balance themselves, they release photons and they release energy in order to become stable, in order to lower down their energy so they can continue to exist, so they can continue to keep the atom balanced. Hence, energy is released in form of gamma radiation. The characteristics of the three types of emission: alpha particles consist of 2 protons and 2 neutrons. It has 4 times the mass of a proton and a charge of 2+. Their speed is about 1/10 of speed of light. Beta particles are electrons emitted with varying speeds. Usually they are very high speed electrons, which can be as high as 9/10 of the speed of light. They carry a negative charge and their mass is the same as a single electron, which is 1/1836 times the mass of a proton. Gamma rays are electromagnetic waves of very short wavelength. They are often emitted at the same time as alpha or beta particles, and these rays are massless. They don't have any mass, although they do have good speed. Ionization power. Ion is a charged atom which is formed by losing or gaining electrons. All three types of radiation are capable of creating ions. Whenever these three types of radiation hit any atom or molecule, they ionizes it. Alpha particle knocks electron out of nearby atoms, thus ionizing the atom. The alpha particles are much heavier than electrons and they can simply dislodge them from atom, thus they have the most ionizing power or potential. Beta particles are less ionizing as they are simply electrons. It is less likely for a lighter beta particle to dislodge an electron, but it does happen. Gamma rays are the least ionizing of the nuclear radiation as they are uncharged, so they are often unable to knock out electrons from a nearby atom. Penetrating power. Alpha particles are the least penetrating of the nuclear radiation and they can be stopped by a single sheet of paper. They can only pass through a few centimeters of air and then they are completely dissipated or absorbed by the air molecules. Beta particles are more penetrating and they can be stopped by a thin, just 1 mm thin sheet of aluminium. The fastest beta particle have a range of a meter or so in air. After that, they becomes completely absorbed by the air molecules nearby. Gamma rays are the most penetrating nuclear radiation. Intensity of gamma radiation can be reduced to half by 1 or 2 centimeter thick lead. This is an image which summarizes all three types of radiation. Alpha particles are 2 protons and 2 neutrons and they have the most ionizing ability but the lowest penetrating power. They are used in the smoke detectors. They are used to keep some types of pacemakers in the heart running, and they are also used in some space probes including the Mars Curiosity rover. The beta particles has lesser ionization ability as they are only high energy electrons. Their penetrating power is also medium. They can be stopped by a millimeter thick sheet of aluminium. They can be used as tracers in medicine to take images of inside the body. They have also been used in cancer treatments. In industry, they have been used to find leaks in underground pipes and to gauge the thickness of material during manufacture. Gamma rays have no mass. They are simply electromagnetic radiation. Their ionization ability is the lowest, but penetrating power is the highest or strongest. They can only be reduced by half by 2 to 4 centimeter thick lead. If you want to completely stop them, you'll have to use at least 4 to 6 millimeter thick lead, centimeter thick lead, not millimeter, sorry. They are used to help sterilize medical equipment. They can also help sterilize packaged foods. Gamma rays detection is used by a number of telescopes to produce images of distant stars. They have also been used in cancer treatments to help kill different types of cancer cells. And with that, I would like to end today's lecture. This is just the first half of radioactivity or 5.2. I'll see you guys in the next lecture. I hope you have understood everything. If you have any issues, please feel free to comment them down. I'll be glad to explain them. If you like this lecture, please give it a thumbs up and share it with your friends. Do subscribe to my channel. Take care. Allah Hafiz.